In this video, we're going to do some examples of Bayes' formula. So first of all, number one says one urn has 4 red balls and 1 white ball. A second urn has 2 red balls and 3 white balls. A single card is selected from a deck, a standard deck. If the card is less than 5, aces count as 1, a ball is drawn from the first urn, otherwise it's drawn from the second urn. If the drawn ball is red, what is the probability that it came from the second urn? So let's figure out what we're trying to find. We're actually trying to find the probability that it came from the second urn. So even though it states red first, remember the probability is what we want to write first. So we want the probability that it comes from urn 2, and we're given that the ball was red. So we want the probability of urn 2 given that it was red. Now, I've got the formula written here, but we're not going to use this formula. I'm going to go down here and show you a diagram that I drew, and I'll use this diagram on each of these problems. So on this diagram here, we draw from urn 1 if we draw a card that's a ace, 2, 3, or 4, because that's less than 5. Now that would be, there's 16 cards that are less than 5, ace, 2, 3, and 4, and then multiply that by 4, and you get 16. So you get 16 out of 52, and if you reduce that, it reduces to 4/13. So there's really a 4/13 chance you're going to draw from urn 1. And since we know we draw from urn 2, if we don't get those cards, then we can just subtract 4/13 from 1 and get that we'll draw from urn 2 with a probability of 9/13. Now if you go back and look at the problem, you know that if you draw from urn 1, if you choose from urn 1, you've actually got 4 red balls and 1 white ball. So the probability of getting a red, given that you draw from urn 1, is 4/5, and the probability that you get a white, given that you draw from urn 1, is 1/5. Now, but if you draw from urn 2, the probability that you get a red is 2/5, and the probability of white is 3/5, because there's 2 red balls in urn 2 and 3 white balls in urn 2. Now, go back to what we want to calculate. We want to calculate the probability of urn 2 given red. Now remember the literal form I gave you, urn 2 given red. So what we do is, for the numerator, we multiply the branch from urn 2, which is 9/13, times the branch that's connected to it red, and so the numerator would be 9/13 times the 2/5. So you can see, there it is, 9/13 times 2/5. And then the denominator is the sum of the products that lead to red. So we actually have the 9/13 times the 2/5, and then the other path to red would be the 4/13 times the 4/5. So we multiply those in the denominator and then add them together. There's the 9/13 times 2/5, and there's the 4/13 times 4/5. And then if you add these together, you get 18/65. If you multiply here, you get 18/65, and then here you get 18/65 plus 16/65, which is 34/65. So 18/65 over 34/65 is 18/34, which is 0.53. So now I'll set up for the second one. So in the second one, it says a small manufacturing company has rated 75% of its employees satisfactory and 25% as unsatisfactory. So we'll call S for satisfactory and S prime for unsatisfactory. Personnel records show that 80% of the satisfactory workers had previous work experience, which we'll call that E, in the job they're now doing, while 15% of the unsatisfactory workers had no work experience, so we'll call no work experience E prime, in the job they're doing. If a person who has had previous work experience is hired, what is the probability that this person will be unsatisfactory? So again, we're looking for the probability of unsatisfactory given that the person had work experience. Okay, so unsatisfactory is S prime. So we're looking for the probability of S prime given E, because E means work experience. So let me change the little diagram here for you, and then we'll see how we can work this. So now you'll see down here I've got this filled out. We knew that 75% were satisfactory, 25% were not satisfactory, and we were given that of the satisfactory workers, 80% have work experience, so that means 20% don't. And of the unsatisfactory workers, we were told that 15% had no work experience, so that means that 85% did have work experience. So now to answer this question, the probability of S prime given E, remember the numerator is the path from S prime to E, so we multiply 0.25 times 0.85, and there you have it in the numerator. And then the denominator, we do all paths to E, so we do the 0.25 times the 0.85 and put that there, and then we do the 0.75 times the 0.8 and put that there, and then you just grab a calculator, do the calculation, and I got 0.26 for that. So that would be, I guess, a fairly low probability. This next one says a basketball team is to play 2 games in a tournament. The probability of winning the first game is 0.1. If the first game is won, the probability of winning the second game is 0.15. If the first game is lost, the probability of winning the second game is 0.25. What is the probability the first game is won? Okay, so we're looking for the probability that we win game 1 if, which basically is the same as saying given, that we lose game 2. So let's just let W1 be that we win the first game, and then L1 lose the first game, and L2 would be lose the second game, and then of course W2 would be win the second game. So we're wanting to know the probability that we win game 1 given that it is known that we lost game 2. Okay, so now let's go up here and look at the table. So up here you can see that the probability of winning game 1 was 0.1, so that means the probability that we lost game 1 was 0.9. And it says if we do win game 1, so if we do follow this path, the probability of winning the second game is 0.15, so the probability that we win the second game would be 0.15, and so the probability that we lose the second game would be 1 minus this, which is 0.85. Then it says if the first game is lost, so if we follow this path, then the probability of winning the second game is 0.25, and then if you subtract that from 1, that tells us the probability of losing the second game given that we lost the first game is 0.75. So now what I wanted to get was the probability of win 1 given lose 2. So remember the numerator, just follow the path from win 1 to lose 2, so that would be 0.1 times 0.85, and that's going to be our numerator, which you can see right there, 0.1 times 0.85, and then all paths to lose 2, 0.1 times 0.85 plus 0.9 times 0.75 is the other path to lose 2. So put that in the denominator, and then grab your calculator and get 0.112 for the answer. So here, to evaluate a new test for detecting Hansen's disease, a group of people, 5% which are known to have the disease, are tested. The test finds Hansen's disease among 98% of those with the disease, and it finds the disease on 3% of those who don't. So in other words, the test is positive on 98% of those with the disease, and it's positive on 3% of those who don't have the disease. What is the probability that someone testing positive for Hansen's disease under this new test actually has it? Now this one's a little bit tricky to read, but what they're asking you is what is the probability that someone has the test given that the test is positive? So basically they want to know the probability that someone has the disease given that the test is positive. So let H be that they have the disease, H prime would be they don't have the disease, T would be that the test says they have it, and T prime would be the test says they don't have it. So basically we want the probability that they have the disease given that the test is positive for the disease. Okay, so I filled out the diagram here. Since 5% have the disease, the 95% don't have the disease. Of the 5% that have the disease, the test was positive 98% of the time, so it means it was negative 2% of the time. Of those that don't have the disease, the test was positive 3% of the time, so that means it was negative 97% of the time. So now if we want to answer this question, we want the probability of H given T. So the numerator, remember, we multiply the path from H to T, which is 0.05 times 0.98. And so when I go back down there, you'll see the 0.05 times the 0.98 on top. And then in the denominator, all paths to T, 0.05 times 0.98 plus 0.95 times 0.03. And so you'll see that down here. So there's H to T right there. And then down here, this is one path from to T, and this is the other path to T. And of course you add those up, and then you divide this, and you get 0.632. I'm just going to summarize this one because this one's very similar to the last one. The only difference is we're dealing with tuberculosis here instead of Hansen's disease. So basically we got a bunch of people here, and we determined that 8% of the people actually have tuberculosis, or I'll just let D be the disease, and 92% do not have the disease. And so if you go back and look at my chart up here, I've got 8% there, 92% there, 8 have the disease, 92% don't have the disease. Now then go back to each subject was given the test, and it says the test was positive in 96% of those who have the disease and positive in 2% of those that don't have the disease. So in my table of those that have the disease, the test was positive 96% of the time, so it must have been negative 4% of the time. Of those that don't have the disease, the test was positive 2% of the time, so it must have been negative 98% of the time. And now what we want to know here is we want to find the probability that they have the disease given the test says they're positive. So if you go back up here, we want the probability of D given T. So we just take the 0.08 times the 0.96 for the numerator, and then all paths to T for the denominator, 0.08 times 0.96 plus 0.92 times 0.02, and that goes in the denominator. And then you just grab your calculator and figure it out, and you get 0.81 for that. I'm just going to show you the branches on this one. Here you can have more than 2 branches to begin with. So let's say the probability A is 0.3, the probability of B is 0.2, the probability of C is 0.5. So this could be like 3 different companies that you're sending samples to. And then let's say the second branch, if you test this you get 0.8 and 0.2 for the breakdown. For the second branch for this one you get 0.6 and 0.4, and for the second branch for this one you get 0.7 and 0.3. So what I want to find here is I want to find the probability of A given T. Now these top branches are T. So this is T, this is T, this is T. They just came from a different branch over here. Okay, so the probability of A given T, the numerator, is just the product from A to T, so 0.3 times 0.8. And then the denominator is the sum of all 3 branches to T. So 0.3 times 0.8 plus 0.2 times 0.6 plus 0.5 times 0.75. And then you get a calculator and figure that out. And I got 24 over 71, and you can put it in a calculator if you want a decimal. Those 2 previous examples kind of shows you how you can test for the reliability factor of a particular test, like a pregnancy test or a test for tuberculosis or something like that. I'm going to go ahead and move on from this video. In the next video, we're going to finish up with just a little bit of statistics.